Yeah, we'll stay for like first 10 minutes to see if everything is okay.
Okay. Nick is coming or?
Is better like that?
No, leave it alone. Yeah, like that is good. Okay. This is working. Nick is not here, but I guess we can begin. Maybe I can say a few words at the beginning. So again, welcome everybody, both online and in person, to this Microstate conference. This year we're doing it in a mixed fashion, and today is the day I want to talk about microstate geometries for non-extremal black holes, spinning and non-spinning. The first talk is by Pierre, and the second will be by Alejandro Ruiperez about this solution. So Pierre, take it on.
Okay, thank you very much. Very happy to be here. It's been for 2 months, so it's cool to have a one talk opportunity. Thank you for that. So as I said, we will discuss a bit of how to build rotating microstates of non-extremal black hole. So it will be a bit technical because it's still kind of work in progress, and we'll see where we are today. So the usual slide to start with. So obviously, it's great importance to find the fundamental structure of black holes. So in string theory, it has been like one of the biggest achievement is from Heidmann counting of supersymmetric black hole entropy. It has been made by counting the microstates turning essentially gravity off by playing with a gravitational coupling. It was a great achievement, but unfortunately, with this profile, we didn't really know what were the black hole microstates where gravity is back on. So there is a microstate geometry program which consists in building at least a portion of the phase space of black hole microstates. We said coherent black hole microstates in supergravity, and all of them are very characteristic properties, which are no horizon and entirely smooth in space-time. So all those very nice program have been led for supersymmetric black holes. So one of the questions we can try to address today is what can we say beyond supersymmetry? So part of my research has been done in trying to understand the microscopic counting of non-extremal black hole entropy. So it's an old subject. We started right after Strominger and Vafa counting for near-extremal black hole, or also assuming non-interacting brane and anti-brane system. So the idea is if supersymmetric black holes are made of branes, non-supersymmetric one needs anti-branes. And recently, I also published something where we try to understand Schwarzschild entropy in terms of bound state of branes and anti-branes. Okay, this is not the subject of this talk. The subject of this talk will be to try to extend the microstate geometry program beyond supersymmetry and build non-extremal microstates of black holes. Again, this story is not very recent. It started with the J-Mart solution in 2005. And then the floating J-Mart turns out there's kind of a large list of solutions, including some of my work, like the static topological star and topological solitons. But the problem is that all of those solutions have some kind of pathologies. the question we will ask is, can we build something non-BPS, smooth and horizonless, a bit like the list above, but there are analytical solution, rotating, and that can have the same boundary, mass, charge, and spin as non-extremal black hole. Those three ingredients are key, and for the list above, JMARC, running bolt, microstate, etc., at least one ingredient there is not satisfied. Okay, so this will be the discussion of this talk. Can we build a framework in supergravity where we can extract such a solution, an analytic solution that are rotating and has the same charge as non-extremal black holes? Okay, so this is the plan of the talk. So we'll start, which is kind of the technical part, discussing how we can organize a supergravity equation of motion and extract solution generating technique to build those new non-BPS smooth horizonless geometry. Then from those solution generating technique, how we can try to build rotating microstates. And I put a very last section at the very end, because it's completely tangential, but I think it's pretty nice, which is a recent paper I published with my PhD student. It depends if we have time. It's kind of a cherry on top of the cake, but completely different from the cake. So we'll see if we have time to discuss that. Okay. So the basic question behind constructing coherent microstates of black holes is we need to solve Einstein equations in classical theories of gravity and construct a solution which has no horizon and entirely smooth. So solving Einstein equations is not obviously an old problem. It's not obviously a recent problem. It has been addressed a long time ago. And one of the very interesting techniques is called the Ernst formalism, which we can review first. The Ernst formalism has been derived for Einstein-Maxwell theory. So we have an action which has an Einstein inverter first, and then just one U1 gauge field added to that. So Einstein equation for such theory is pretty nasty, but Ernst showed that if you take solutions that are only depending on three coordinates, so three space-like coordinates, things organize much nicely. So essentially, if you take solution which you have static, so it's just dt squared, you have a 3D base which is ds3 squared, and a gauge, a field strength which is purely electric, dt, where t is a gauge potential and t is time here. You have a problem which you have essentially two fields, z, which is a gravitational potential, and t, which is an electric potential. Everything depends on the 3D coordinates, ds3. So Ernst showed that if you plug that in the Einstein equation, everything organized nicely. It's still nonlinear equation, but it's a solvable equation. It's called the Ernst equation, static Ernst equation. So it has been greatly analyzed in four-dimensional GR. Many solutions have been built, and this has been a successful story. So the thing I've done like a few years ago is essentially try to extend this solution generating technique, this framework, which is only for 4D GR, to supergravity theory. So obviously it's much harder. So for instance, if you take 5-dimensional supergravity n equals 2 to 5D supergravity, you have still an Einstein invert term. You have three scalar, which are parameterized by this x. You have three gauge field, U1 gauge field, which has this f. And you have a Chern-Simons term on the right-hand side. And this Gij is a coupling that depends on the scalar. So it's much nastier theory. But at the very end, you can try to do the same as Ernst. So you restrict to solutions that depend only on three coordinates. So it's time invariant. It's static, so you just have minus dt squared. It's pretty much the same as in 4D. You have more z, essentially, more gravitational potential z. You have four of them, z1, z2, z3, and z0. You have a fifth dimension, which is here called psi. So you have more ingredients. The gauge field, we will assume to be purely electric, so you have three of them.
There's 1/3 in the second part, right?
dt
squared over 2.
Oh, yeah, it's 1/3 here, sorry. And you have three scalars which depend on this gravitational potential. So this is a generic ansatz you can plug. And there is a kind of miracle happening here, is that the Einstein equation for this setup is exactly because you have four z's, four decoupled static Ernst equations. They're completely decoupled. It's exactly the equation you get in 4D, but now extended to 5D supergravity. So what does that mean? It means that we can use all the work that clever people did in GR, solving those static Ernst equation, but now inside supergravity, where you expect more solutions, and build interesting objects like static non-BPS smooth horizonless solution. So this is really the framework. Just saying that without supersymmetry, you can still solve Einstein equation in supergravity using known result that has been done for DGR. So this story worked very well, and it's only static. So the question is now we want to address the problem for rotating object. So we can again look what has been done in 4D Einstein-Maxwell. So you take the same theory as before, but now you assume that you can have stationary solution. So you have essentially a one form omega t here, which can be turned on and will obviously complexify the equations. In a sense, you have more field. You have the z, the same guy, t, the same guy, but you have the one form omega t. So for 4D Einstein-Maxwell, Ernst has also studied that. It gives equations which are similar in structure, mathematical structure, but it's just complex now potential. But at the very end, it has been studied a lot, and everything also have been pretty successful.
There's no magnetic pieces?
No, I mean, you can add actually. You can add an electromagnetic dual guy if you want. It's not a big deal. Here, yeah, for simplicity, I take it off, but you can add it. But you can also keep it away.
You have rotation and
I mean, you are
rotating electric charge, then you have a magnetic field. So
yeah, actually, maybe you might need a guy here. Yeah, yeah, I guess so. For obviously for 5D supergravity, I am. So now the question is, for static, it was super successful. What was successful is we have been able to take an ansatz for 5D supergravity and shows that it gives multiple decoupled Ernst equations. So here is the same question. Can assuming a generic supergravity solution depending on 3 coordinates, which is stationary, can we obtain something where it decoupled into multiple Ernst sectors? The answer is no, obviously. Not obviously. I mean, it makes sense because you have a lot of electric and magnetic fields that couples together, so you don't expect decoupling different sectors. So here we cannot use the previous trick where supergravity equation of motion were essentially 4D Ernst equation. You need something else. But the equation of motion that arise for solutions that depend on 3 coordinates have been studied. It leads to an integrable sigma model in supergravity. So it's not completely hopeless, essentially. We cannot use the result of 4DGR, but we can use some solution generating technique. So here I will just review the sigma model of 5D supergravity, which can extend to also M theory, type 2B, it's pretty general, and how it works. So essentially you take the action of whatever supergravity theory you like. So here I took 5-dimensional supergravity. So again, just to repeat, you have the Einstein-Hilbert term, 3 scalars, which are x1, x2, x3, 3 gauge field f1, f2, f3, and Chern-Simons term. So the idea is you will assume that solutions are stationary. It doesn't depend on time. And it has also an extra isometry because you're in 5D. It doesn't depend on size, this extra circle here. So the generic ansatz you can have is pretty much similar as the static one I showed before. You have 4 Zs, which are gravitational potential. You have an electric gauge potential. But now, because you allow stationary, you have this extra guy mu, which is momentum along the 5th direction. You have the one form omega t, which is angular momentum along the 3D base. Here, omega psi is also another one form. So this is the most generic thing you can think of. And you have at the very end 16 fields. So the way to derive a sigma model is to reduce along the isometries, which are t and psi. The best way to do that is first kind of take a universal frame where you don't have one forms and scalars, but everything is scalar. So you can dualize this omega t, omega psi, and ai here, which is also one form, into scalars, so that you get 16 scalars, the z, the gauge potential at, a psi, and then bi, which is a dual of ai, capital omega t, which is a dual of small omega t, and capital omega psi, which is the scalar dual of omega psi. Then you reduce along t and psi, and you get an action, which is essentially an Einstein-Hilbert term coming from the Einstein-Hilbert term in 5D, plus 16 scalars, which are non-trivially coupled, obviously. And the coupling is depending on this JAB here. So this JAB is called the target space of your sigma model. So this is a sigma model, essentially. Sigma model is gravity plus scalar field. The scalar field has a non-trivial target space, which is captured by this metric GAB, which is 16 by 16 here. Okay, so in many theories, this target space has some symmetries, and symmetries are very useful. Here I will come back to that, but we can understand how useful it can be. Essentially, if let's say you have some group of symmetry for GAB, such that if you take an element of the group, if GAB is invariant under this change, this transformation, what it means is if you start with a solution phi A, 16 vector corresponding to a solution, you can obtain a new one by just multiplying by G. So it's pretty useful. Why? Because you can start with a solution we call a seed solution, which let's say it's vacuum, for instance, so there is no gauge field or anything. Let's say G is a weird element that can shuffle those scalars together. You can obtain a new solution with completely different field content. So that's one of the tricks of this sigma model. If you have a solution, and if the target space has some symmetries, you can obtain new ones pretty easily. Okay, so how to organize this thing more precisely? The way to do it is usually we don't work with this 16 by 16 matrix. It's pretty ugly. So what we do is we essentially reorganize the scalar target space in terms of a coset matrix M. So here is just a reorganization of the thing. The equation of motion of 5D supergravity in this framework are pretty simple in terms of this coset matrix M. It's a simple kind of scalar equation of motion at the beginning here. And the 3D base is sourced by this non-trivial matrix M.
So,
yeah.
Because that's what SO44
for 5D supergravity. Yeah, I'm just right here. Yeah.
the action was going to
Really, the symmetry of this coset matrix M is really what characterizes the sigma model and also characterizes the supergravity theory you start with. So for 5D supergravity, as Nick said, the symmetry group is SO44. So it's an 8 by 8 matrix M, and you have this SO44 symmetry group. But if you take 4D Einstein-Maxwell, we could have done exactly the same process here. We would have obtained a coset matrix M, which is 2 by 2, and it has an SL2R symmetry group, which is typical of the Ernst formalism.
That's the Ehlers group, isn't it?
Alien?
Ehlers.
Yeah, maybe, yeah. Whatever name, you know.
Ehlers is the first guy.
Yeah, we should think that. Then if you take 5D minimal supergravity, which we'll do in a moment, it's just a truncation of 5D supergravity where all the scalar fields are trivial and the 3 gauge fields are equal. It goes from SO44 to G22, which I don't know what it is, whatever. And finally, you can just for fun ask like, what happened if you don't take 5D supergravity, but 5D Einstein-Maxwell, which is pretty much the same, but you don't have Chern-Simons term. Actually, this is a very bad theory in many aspects. The target space has no symmetry, so you cannot build much thing in this theory. Actually, it's kind of open question. The black holes here is pretty complicated. Not 5D black holes, but 4D times an S1 black hole is pretty hard.
So if you don't have the Chern-Simons term, you get a bad theory.
Yeah, you cannot do anything.
So I remember a long time ago, I had discussions with these people, and they were working in 5-dimensional SO44 theory, and they were saying the Chern-Simons, we don't know how to incorporate the Chern-Simons. So
no, you have to. Like if you really do like this kind of process for 5D supergravity, the coset matrix is disgusting. The symmetry there's nowhere.
Exactly the thing you get with the Chern-Simons term.
Yeah.
That's so for you.
Actually, it's essentially it's more fundamental with the Chern-Simons. For instance, if you take resonance from 4D and you try to embed in 5D, you need Chern-Simons. Otherwise, you cannot do it. Anyway, so now we are done with the sigma model. This is a sigma model of 5D supergravity. What can we do out of that? We can build solution generating technique. One is the one I was saying before, using the symmetry group to build a new solution from a seed solution. So let's say you start with a known seed solution, whatever solution. You can take either the Bénard-1 or BPS solution. You can take Euclidean Schwarzschild. You can take Schwarzschild, whatever seed solution that you already know. So it's characterized by a M0 of the 16 scalar field, a base, DS3 square. Then you can take any relevant SO4, 4 matrix you want. I will call it G. And then you can just build a new solution by just a matrix product. It cannot be much simpler than that. You just take an M, which is multiplying M0 by G transpose on the left and G on the right. DS3 is conserved because of the equation here above. So you will get the same 3D base, and you will have a new solution. The process of this is very easy to construct. Like you don't even solve any differential equation. You just take one and you do matrix product. Mathematica can do that in a few seconds. The cons is essentially you preserve the 3D base. So if you start with a solution that have, for instance, 3D base which is flat, like BPS solution, the new solution will be also flat. What does it mean concretely? It means that you cannot really create new source with this method. If you start with a solution that have like 5 centers, the transform solution will have also 5 centers. Okay, other solutions that we discussed in the paper is essentially inverse scattering that you can also apply to this matrix M. We didn't really do it, but it's something we can think of. Okay, the process obviously here for the inverse scattering is it's more complicated, obviously, than this matrix product, but you can generate new source. So you can change the base. You can go from a solution with 0 source to 5 source and stuff like that.
That's the question I think I should have been asking. So can you generalize these inverse scattering methods to theories with Chern-Simons interactions?
Yeah.
That was the hard thing.
Yeah, that's
I mean, as soon as you have
still harder. Nobody has done it yet. I mean,
But has he done it? Have you done it?
no.
Yeah, I mean, I never applied it, but you like inverse scattering only require this thing. As soon as you have such a thing with M1 here, M there, you can do anything. You can apply inverse scattering.
Sorry?
Yeah, I mean, it can be a 1 hour talk, I guess. It's a method that initially has been built for vacuum GR 4D, which like you have a metric, which is the main element, and from a seed solution, which is usually trivial, like flat space, inverse scattering is you introduce a spectral parameter, and playing with that, you can essentially get many solutions without solving equations. But there is like many steps to the thing. But for instance, people have shown that from flat space using inverse scattering, you can get Schwarzschild, Kerr, anything without solving anything, without solving Einstein equation. But it's kind of a complicated step. Like you introduce a spectral parameter, you do a lot of things.
I just wanted to, it's been a long time since I've talked to people about this. I always thought that the gravity thing was the standard thing you could do inverse scattering with, but Chern-Simons was something that hadn't been done. And that's
so here, I mean, so if you take vacuum, any kind of vacuum theory of gravity, any dimension, the sigma model you get is actually this one where M here is replaced by the metric along the extra dimension. Like for instance, if you take 4D, let's take 4D GR, you compactify along time. Here, this will be a 1 by 1 guy where it's just GTT, essentially. GTT, yeah, you have a bit more guy. And then you can apply inverse scattering on this matrix G, which would be the metric. If you have more scalars on top of that, here is not the metric, it's M, it's coset, but at the end you can apply still the same thing. The only thing which may be complicated is here this M needs to be SO4,4 symmetry. It needs to belong to SO4,4, the group. So when you do inverse scattering, you will have extra constraints so that the M you obtain is SO4,4. But not in purpose.
especially what we used to have about.
We talked about
Yes, exactly.
Yeah, but he published a paper about that actually, like, and he did the inverse scattering process.
I thought it was a really hard problem and it didn't go very far.
It's hard to apply. It's hard to apply, but the technology works. The only problem is like at the very end, if you inverse scattering give you a new solution, but you need to make this new solution belong to SO4,4. So you have a lot of constraints. While for vacuum GR, you don't need the new solution to belong to SO4. You just want a symmetric matrix, which is much simpler to model. I mean, we can discuss
we're
that.
planning for a long time to do, for example, multi-bubble J-mart. So J-mart with multiple bubbles. No, I don't think we can ever do it because I mean, inverse scattering in principle, take a J-mart, you find as a seed, and then put another one and build a multi-J-mart configuration with inverse scattering.
I mean, probably you can do it, but you need to be a bit smart. Okay, so I will not do the inverse scattering method, but I will do this SO4, transformation and show how it can work. So the idea is you need to start with a seed solution. The best example of seed solution we can think of in 5D is a vacuum solution, simpler. And here we'll take the top bolt geometry, sorry. The top bolt geometry is just essentially the weak rotation of the Schwarzschild nut black hole. With a time, essentially you double weak rotation, so essentially you have a minus dt square. Delta here is a bit like the Schwarzschild factor when you have a nut. It's r squared minus 2mr plus n squared divided by r squared minus n squared. And if you take n equal to 0, you retrieve Schwarzschild essentially. And then you have a nut charge, which is parameterized by n. And the small parameter m here is associated to the mass essentially of the object. So it's a perfect valid solution of 5D supergravity, obviously, because it's a vacuum solution of 5D vacuum Einstein. So what you can do is take the M of that to derive the coset matrix M. It's rather complicated, but at the very end, it's a matrix which is sourced by two monopoles. We have a monopole coming from the mass M and a monopole coming from the nut charge N. So using this SO4, 4 transformation, we can shuffle this monopole. It means like it goes like n over r stuff, or n cos theta.
Well, not talking about a monopole, I'm thinking about a very particular SU2 structure.
There, deep psi plus n cos theta d phi. So that's deep psi plus 2n cos theta.
No, I understand
So
that.
that's
I understand on the nut, but it's the mass becoming a monopole.
Yeah, it's actually, I didn't know about that, but when you derive M, the mass and the nut comes at the same place, kind of.
It's in the same footage, so
Yeah, I see.
the mass is a
Like for instance, you can derive the dual of M0, the one form, you will get n cos theta terms and m cos theta terms. Mass is really a monopole charge at r equal to 0.
Is it a different circle being Feynman or?
It's not a circle, it's just.
No. Okay, the monopole, you have a psi fibered over a base. So that's the n. So the psi is the fiber. So does m have some other circle vibration?
No.
So why is it a monopole?
I mean, you compactify in 3D, so like T and psi, what comes from T and psi are kind of unified.
So
And M,
T is being fibered with the mass, is that it?
yeah, I mean, like M is really like the thing you obtain when you compactify on T and psi. And when you do that, M and N comes like monopole terms.
Okay, this is a non-trivial vibration of the T over the base, is that?
Yes.
But not really, I mean, it's just minus dt squared. But
No, there's not fibered, okay.
No, but
Every time you say yes, you say no, and every time you say no, you say yes.
Now there is none, but when you mix the will be, and then you need to put it to 0 to avoid cross-term occurs. So at this point, there's no T vibration.
Right.
When you start mixing up, you get a T vibration.
yeah.
So you get the equivalent of the monopole for the mass, and then you have to put it to 0
Right.
to get a clean solution.
Good.
But mixing, there's democracy between M and N.
At the very end, when you really write M0, you see that there is kind of every time M comes and M comes at this like same functions around. So there are two really monopoles. Well, if you have like a spin, it will be a dipole kind of. Okay, so an important part of this is like if you want to use SO4 transformation to generate new solution, since the 3D base, which are here given there, will be conserved, it's very important to have a seed solution which is smooth and horizonless. Otherwise, you will have problems. So we need to make sure that the solution we have here is smooth. So topnet, it's pretty nice. Everything is you can make everything smooth by just imposing a periodicity lattice of psi and phi, which are completely independent, but it will be important in a moment when we'll do rotating solutions, where you have 2 pi r psi 0, which is one periodicity for the psi circle, and phi is 2 pi period. So having this periodicity is compatible with having asymptotics which are S1 times Minkowski, and also compatible with regularity at delta equals to 0, which is a place where the psi fiber degenerates. Okay, so now we can take the SO4, 4 group. It's a 28 parametric group, so it's pretty big. But we want to use the transformations that preserve asymptotic flatness. Obviously, we want a solution which is still asymptotic to S1 times Minkowski. So this reduces the size of the group. So the size of the group we identify, which preserve the asymptotic of the solution, is 12 parametric, and we decompose in 3 times 4. You know how to count. The P group, the W group, and the Z group. And now what you can do is take this M0 multiply by any element of those groups, and obtain new solutions. So we showed that first, the topological star I constructed with IBU is simply the P group applied to this guy. So you can obtain the M of the topological star by just multiplying by a GP of this SO4 command for transformation. Then we build new solution I will summarize in a moment, which can be considered as W topological star, where you apply the W group element on top of the top bolt. And you can build more generic topological star. It will be uglier and uglier as you apply more elements. But at the very end, you can have a very complicated multi-parameter solution. Okay, so I will just briefly summarize the W topological star because I think it's much interesting than the previous topological star I built. So in the paper, we wrote it as a 5-parameter solution. But here I'll just show when we take all the charge equal in magnitude. So it's a solution that has 8 charges. Like topological size was only 3 charges. Here it's 8. So it has a KKM charge, Q cos theta. It has an electric momentum here, Q over R dt. It has an electric charge in the gauge field. So because we took equal charge, there is only one gauge field. It's minimal supergravity. There is a magnetic charge, Q cos theta, and a Maxwell charge also here and there. But at the very end, the solution is pretty simple. And it even looks like Rassmann-Nordström in some aspect. Like, for instance, this coefficient is very close to Rassmann-Nordström. And the validity of the solution require M to be larger than a certain extremality bound, which is square root of 2M bigger than Q. If you assume that, you have essentially, when this polynomial here is 0, you have the psi circles that shrink, and you can compute everything. Everything can be made smooth if you impose R psi to be something.
So R squared is equal to 2Q squared?
It's never actually. It's sorry. The first root is this one. If you take this square root of 2M bigger than Q, this one will be smaller than the first root of this guy.
Okay.
So it's closing off before.
Closing off before.
That's why, like, it's true. Like at R squared, if you don't allow this bound, you indeed can have R equal to square root of 2Q before the thing, and it's pretty bad.
And R equals 2M is where?
It's even before. Like the first, like this bound is really made so that the first root is this guy.
Okay.
So that and this 0 is perfectly smooth. Like you can see, it's kind of Schwarzschild like, actually more like Rassmann-Nordström. Yeah, Schwarzschild. So the solution is entirely smooth, and you just have a regular circle pitching at R equal to whatever value given by this root. So the thing which is nicer compared to the previous solution I built with IBU 6 years ago, is that it has 8 electromagnetic charge. I don't know if it's a good point actually, but it has 8 electromagnetic charge. So you have non-trivial Chern-Simons term contributing here, and it makes a better link to the BPS solution Yosif and Nick built a long time ago. Also, it has a top bolt structure. In a sense, it has a KKM charge. And this is actually important for spin structure. Euclidean Schwarzschild has no spin structure, and topological star I built with IBU long time ago might have no spin structure too. This one should be fine.
So what are the 5 parameters? I can see M and Q. What else?
Yeah. So here I'm just taking one equal charge.
Like flux is on the
So
bound.
3 Qs.
If you use
M.
when M and a D6 charge, don't forget there's a fiber.
Yeah.
D psi plus Q cos theta.
It's actually like a big Gibbon-Sucking center. Like a Gibbon-Sucking center, you have
If you start with the spacetime which has a spin structure and you apply those SO44, you still preserve a spin structure.
No.
Is that the true state?
I don't know.
I don't think so.
That's what you did, right? So how do you know you have a spin structure?
I mean, it's maybe I mean, here the problem with spin structure is really when this circle pinch is off, like this guy. Like you look close to R equal to where this is 0, and here is actually like a top bolt. The geometry.
Okay.
So I guess maybe
It closes like top bolt,
Yeah.
double bolt. Okay, I see. Okay, thanks.
When you have this Q, for every even Q, you have a spin structure, and for all Q to don't, or vice versa. So we
Yeah,
have some around, and but you always have it for some. If you don't have any Q, that's bad. But if you have any Q, if you have Q which is finite, then for half of them you have a spin structure, for half you don't.
Yeah.
You always bump some to somebody.
C structure. Okay. Have you re-identified any lattices of charges or lattices of You had a periodicity of phi and psi.
Yeah.
Have you redefined those periodicities, or is it still the same periodicities?
No, indeed, here, like arm side, the periodicity of psi needs to be fixed in terms of mass and stuff. Not really.
So what has to be?
There is a constraint between arm side
Oh, I see, yes.
and the mass and the charge. Yeah.
But you haven't redefined the lattice of periodicities, right?
No,
You scaled the lattice.
I'm not sure I understand what you do.
Okay. You had a periodicity of phi being 2 pi and psi being 2 pi r.
Yeah.
Have you mixed phi and psi?
No, that's the thing.
So
Yeah.
what have you scaled?
Yeah, that's why.
But that's fine. That's
Yeah,
fine.
I really
Because
impose this.
you can screw up the spin.
Yeah,
structure.
actually, I will discuss that.
You can screw up the spin structure by redefining.
Yeah, it's been. Yeah. No, here I didn't do that. Okay, and also another good point is that the extremal and BPS limit is perfectly well defined here. It's actually a Gibbon-Hawking center. Well, for the topological star, it was the microscopic like singular black hole. Here, this one is really a nice Gibbon-Hawking center. If you take m equal to q over square root of 2, it gives solution that Nick and Yusuf know very well. Okay, and also you can build a black hole which has the same charges as this one. It's not a Raison-Nordstrom black hole. It's a bit weird why, but it's just because of sign of charge. Some charge are negative, some are positive, a bit like Gibbon-Hawking centers. So the black hole is actually not the usual Raison-Nordstrom, but you can compute the black hole solution. It's also a nice solution to study. Here it's exactly the same charge as the guy above, but the thing is the coordinate singularity is at r equal to 2m, and it's the times that shrink, so it's really a black hole solution. But this object has exactly the same charge as this object. So you really have a smooth horizonless geometry, like this W topological star, is the exact same regime as a black hole, and maybe you can consider it as a microstate if you want. Okay, so this is for static solution. Now, how can we use this technique to build rotating solution? So it seems very easy. Before we use a top bolt geometry, which were static. So now we just need to use a geometry which allows spin and use transformation to generate this spin. So we can just consider not top bolt, but Kerr top bolt. The Kerr top bolt is pretty much the same solution. You have m and n, where n is the net charge, m is the mass. But you have a parameter a, which was a spin of Kerr. But because you rotate, it's not a spin anymore, it's a magnetic dipole. But you have this solution, which is a vacuum solution of 5D Einstein theory, so 5D supergravity. And you can use that to generate rotating solution. Why? Because essentially, if you derive m0 for this guy, you will get also 2 monopole charge, which is the mass and the nut, and 1 dipole charge, which is A. And by applying these SO4 transformations, you will put the A elsewhere in the field so that you might make something rotating. So here there is a problem, which is a bit related to what Nick was saying, which is about the periodicity lattice. When you work with Kerr top bolt already, there is a certain conflict between having a periodicity lattice, which is asymptotic to S1 times Minkowski, which essentially requires that the psi and phi periodicities are untwisted. But problem is the regularity at delta equals to 0, which is where the psi circles shrink, usually impose something which is twisted, whereas this coefficient alpha here is smaller than 1. So how can we resolve that? We will see in a moment. So first, we will try to understand what is the problem of something that has twisted periodicities in terms of asymptotics. So let's consider flat space. So this is very simple flat space with an extra S1. But we will not assume untwisted periodicity, but we will assume that there is a twist here, 2 pi over k, when you move alongside. So first, it looks like flat space, obviously. It looks like Minkowski times an S1. But this part here essentially makes this Minkowski times an S1 a Minkowski times an S1 divided by mod Z and K. So you can come back at the same place if you just turn around the S1. What is this space-time? It's actually a very bad space-time. It has been studied by Docker, Gauntlet, Gibbons, and Horowitz in 95. And it's called the magnetic flux tube. But just to show how far from flat space it is, we can just describe it. Essentially, what you need to do is rewrite the flat space metric here in terms of independent orbits. So the independent orbits from this lattice is psi first, but also this phi tilde, which is phi plus a twist alongside. So those are the angle which, if you move along one direction, you don't move along the other direction. Now, if you rewrite this beautiful flat space metric in terms of psi and phi tilde, you see a lot of problems happening. First, you have a blowing dilaton. So you go to a cylindrical coordinate rho and z. So rho is really the radial coordinate in cylindrical coordinate. So you have a blowing dilaton along this psi direction. You have a magnetic field which is constant asymptotically, and you have a finite size of the phi circle. So it's nothing like flat space at all. So the problem is really working with the Kerr-Tor bolt, which is necessary to build rotating solution. You need to force your Kerr-Tor bolt to have this periodicity of lattice, this periodicity lattice. It's really something you need to impose if you want to have something which is compatible with Minkowski times an S1. And doing so is a very strong constraint on the parameter, which is given here. So the spin parameter A, the mass and the charge needs to satisfy this quantization. So it's not a problem for A equal to 0, which is the case we've studied, static. Obviously, 0 is an integer. But as soon as you turn A, you need to satisfy something which is pretty dramatic. If you want this quantity to be an integer, M, essentially the mass, needs to be smaller than the charge, N. So you will start with a seed solution, which is outside the black hole bound. Just by turning A, we need to have a seed solution that is outside the black hole bound.
How can we see that K is equal to 1? I didn't expect it to be problematic, but
I mean, here, like if let's say if M is bigger than N, this is larger than the top.
Yeah. No, but from solution above. Okay, K.
I know it's very hard to see why this arises.
Yeah.
Yeah, I skipped really need to work with the Kerr-Tor bolt and see how can I impose this lattice. Essentially, you really need to force 0 here. It's really not to be a complication.
Yeah, but 2 pi is not even enough. Like
actually, 2 pi is completely equivalent to this one.
yeah. So
And if I have 2 pi, K is bigger than 1. Sorry.
Yeah. So if K is equal to 1, it seems that the metric is still kind of very weird.
Not really. Yeah.
It is, but the solution is the same. So you're compactifying from M theory with a Melvin twist of 2 pi, which is the same solution. Now the metric appears to be very weird, but if you don't look at the same theory on K equals to 1 space, it's exactly the same spectrum as if you have K equals to 0. It's a very weird phenomenon that you have the space times, and then when you put K and you change the angle, when the angle becomes 2 pi, you get exactly the same. You get a very weird metric if you just compactify on the wrong direction, but you have the same.
Yeah.
You have the same spectrum.
You can have a look to the Docker paper. It's actually very nice and everything is.
But it's called the Melvin universe, by the way.
Paraphrase what you've done here. So basically, you've got an infinite circle that's staying a constant size and a circle that's blowing up. But if you do this weird twist, you have to mix them up, and then you've got two circles that are blowing up at infinity. But then you can, if when A is chosen to be the right discrete value, you can then untwist that and wind up back with a circle.
Yeah, kind of. I guess so.
That's good.
Okay, so I think Alejandro will talk about them. And you can still build solutions which have twisted periodicity. Nothing forbids you to do that. And it's actually very interesting. You can get the solutions they build, which are rotating topology per star, which essentially solutions that can be constructed from SO4,4 transformation of the Kerr bolt, so n equal to 0. But the problem, even if it's a simple solution, is they are asymptotic to a magnetic flux tube, so it will have certain pathologies compared to what you expect if it's our real world. But I'm sure Alejandro will talk about that. So you can still build them, and they are very interesting. But at the very end, to talk about black hole microstate, you need at least something which is asymptotic to R1,3 times S1. Okay, so I mean, I will not show the solution we will build with Pani and Santos because still in the project. But what we've done is essentially we impose asymptotic flatness, so it requires the mass to be smaller than the charge. So we are outside the black hole bound, but we can still build solution in there. So they are very interesting properties. So they are first asymptotic to S1 times Minkowski. They are smooth and rotating, so it's kind of an achievement. Unlike J-Mart, the spin can be very small, so the spin is not a problem here. It's not over-rotating. There is no ergo region for a lot of parameter space. Perturbation can be studied very precisely because everything will be separable like Kerr. And some stars we've been building are very close to the black hole. Even if they don't have the same mass and charge as the black hole, they can be made very, very close to the extremality bound. Obviously, the cons, and it was pretty disappointing, is we are outside the black hole bound, a bit like J-Mart. We still have no example of rotating solutions that are really the same mass, charge, and spin as black holes. And there are many parameters involved Sorry, they are more complex than the solution Alejandro will talk about. Okay, since I guess I'm running out of time, you will not have the cherry on the cake. I guess I have.
You can go, I mean, you know, the beginning to
Show me
15.
the cherry on the
Okay.
cake. I mean,
Okay, for me, this one is the
You have 1 hour, so in principle,
Okay, good.
you have 1 hour.
Okay, so it will be perfect in 10 minutes.
Possibly 15.
Okay, here is completely tangential move, but I think the project is pretty cool, and at least it's less technical than Sigma model. But so it's a project I did with my student, and the question was a question that actually Nick tried to address for supersymmetric solution. So it's completely different from what we saw, but it's a question that essentially the first bulb or the microstate geometry program needs to answer, which is if you consider black holes as an ensemble of horizonless state, how can smooth horizonless geometries generate something that has absorption features? So what can be a mechanism? What mechanism can arise from those very weird, highly redshifted geometries which are smooth, so that if you send something in, it will be something somehow trap what it should a priori evade, just because it's like if you send something close to the sun, it's sufficiently kinetic energy, it can just evade. So what happened for those guys? So it's a question that has been addressed by Nick for supersymmetric microstates.
Emil too.
And Emil also at the beginning, I guess it was, yeah. Okay, Emil is coming at the very end step. So I just wrote the first paper because there's many papers. So the question is, what has been shown is essentially the key point, which seems to differ from black holes to those smooth horizonless geometry, is tidal stress. So it has been shown that if you send a particle inside those smooth horizonless geometries, which here are superstrata, extreme tidal stress appear way above the cap. So the way above the cap is pretty weird, but it's still there. Do you expect any kind of probe that has internal degrees of freedom, so I don't know, a football or string or whatever, that this extreme tidal force will excite internal modes of the object so that it will drain kinetic energy, take the kinetic energy of the object, so you will expect a trapping. So then with Emil, they have shown that if you do actually string propagation, so it's really an object with internal degrees of freedom, you send it in, this extreme tidal force will essentially excite internal modes of the string, so you will have a mode production, so that kinetic energy are drained out of the string. And if you try to measure how much modes has been produced and find the effective mass of the object that is generated by this mode production, you will find that it reaches a maximum height and go back in. So this is a very successful story for supersymmetric object. There is one weird thing here which maybe try to correct, which is the fact that everything happened way above the cap, which is not something we expect. Like the cap is a new thing. Wait, where am I? Yeah, I lost it. So for the black hole, the horizon is here. So you expect all new physics to be very down there. Here it appears to be way above. So it can be a feature of atypicality or anything like that. But what we will do is exactly redo this very nice computation, and now in context of the new solution I've been building, like this topological static solution. So we can readdress this question, but now we consider not the supersymmetric microstate, but non-supersymmetric microstate, which are actually like Schwarzschild. So they are entirely neutral. So it's a neutral bound state of two topological stars on a vacuum bubble. So it's fully smooth. There is a cap replacing the Schwarzschild horizon. So yeah, the thing we have done is essentially we didn't really take the full smooth solution. We took a simpler guy where it's a big fat smooth bubble, but the topological stars at the edge of the bubble have been replaced by extremal black holes. So they are still black holes in the geometry, but it's smooth everywhere. The reason why we've done that is essentially the solution I built with Hebrew in 22 is ugly and disgusting, while this one is much simpler, so you can really do geodesics computation a bit nice here. But now you can do exactly the same question that Nick and Emil and postdocs have tried to address. First, we discuss what are the trajectories of infalling particles. We observe that, okay, here is just to specify, like this geometry is pretty weird. Here is just because we took ACMC coordinate of the system. So the black holes, the point here are the black holes. But because we are in ACMC coordinates, they have been pushed back outside the poles. And all the blue and green line here are smooth locus. So trajectories of infalling particles is mainly radial, like Schwarzschild, as you expect. But because we have a non-trivial cap here, you see some attractive mechanism from the black holes here that attract the thing. But you can also bounce on the bubble non-trivial. So essentially, on the equatorial plane, everything bounce and escape. So we have a geometry which is essentially capped at 2m plus epsilon, where epsilon is given by some extra dimensional size, arc psi. Trajectories are mainly like radial, like Schwarzschild, and we have non-trivial attractor due to the black hole. But if you replace by superstrata, for instance, it will not be absorbing at all. Now about tidal force, we retrieve exactly what Nick observed. So depending on the release angle, we have very different tidal force. But the important thing is essentially the maximum tidal force we observed on the equatorial plane, scaled with the mass square times epsilon 5, which is the resolution scale of the cap. So epsilon is really upside times m. It's a very small quantity, and it's really the Kalos-Decline scale. And this maximal tidal force that the probe is experiencing is much larger than string scale when the mass satisfies this very loose bound, which is very easy to satisfy. So for a massive object, tidal force experienced by the particle will be huge compared to Schwarzschild. So then we did.
Where is the tidal force being experienced?
It's like, yeah, so that's an important thing. You see, it's growing kind of progressively. So like here is R over 2m. So 1.5 here is the 3m, is like the photon sphere. So it's really growing like a polynomial, actually. It's a power 5 polynomial. But it's still, it reached string scale only incredibly close to the cap. So you need to be epsilon away from 2m to experience string scale tidal force. So this is a new thing, which will be summarized here. All the extreme tidal force, extreme stuff are really localized at the cap.
Now, this is happening far away from the black holes. You have a black hole at the North Pole, you have one at the South Pole.
Yeah,
You're bouncing on the equator where nothing is. I mean, just a stupid bubble.
Yeah, I mean, I took this black hole bound state just to have something where I can actually do anything.
But the place where you get maximum tidal force is actually in the middle.
Yeah.
It's in the bubble.
But actually, you should expect to get extreme tidal force here if you replace by a bubble too.
Yes.
The fact that they reach small value here just because they reach the black hole.
What's setting the scale where you start divergent string scale? Is it Planck or is it?
Is the scale is Kalos-Decline? It's upside. Is a Kalos-Decline scale.
That's good. Perfect.
But the thing is, yeah, actually, it's a point which.
That's lovely. That means
The thing which is important, actually, I forget to say that, it's very important. Like it's very huge. It's m squared times epsilon power 5. But if it was 3, epsilon power 3, which is pretty huge also, it would not work. It would not reach string values.
You hit the bounds.
So if you take epsilon,
so there are two things going on here. One of which is the actual tidal force, and then there's the impulse delivered by the tidal force. In other words, you take into account the time it's actually feeling that force.
yeah, but if the tidal force is not even string values.
What is the reach string value? It sounds like epsilon goes to 0.
So the other thing, like if the mass, okay, sorry, it's very small. I didn't notice, but if the mass is bigger than arc psi over ls square, so the ls comes here times arc psi, this m square epsilon 5 is much bigger than 1 over ls square.
Okay.
And you see that if you take arc psi to be 10 times the string length, you just need a mass which is 100 times 1000
What is
times.
epsilon?
Epsilon is the Kalos-Decline scale, which is arc psi over m, power 2/3, some power, which is due to the geometry. It's really something given by the fact that it's smooth. So everything is set by the Kalos-Decline scale, but in such a way that it's still string scale.
Well, okay, so the difference in the work that I did with graduate students earlier, and then the stuff with the meal is you have this super string scale force, but if it doesn't act, it's not going to do anything.
Yeah, and this is the next part.
Okay.
I mean, I didn't show the computation, but actually it's what we had. We then did the string computation you've done.
Yeah.
And indeed, we get extreme tidal force only localized here for the string. It starts to produce modes only.
Impulse. Is it enough?
Okay.
Is it enough?
And it's enough. It's actually exactly the same thing. And it's actually enough and also better in the sense that it's such a way that the bounds will never go above 2m plus 1 plus epsilon. So you can really do the computation. I mean, I've been copy pasting your thing essentially in this context, but here everything works beautifully so that everything is confined at the cap completely.
And the scale of the set out.
All the scales are really either string scale away from 2M, either KK scale away from 2M.
You say it's the Pulitzer-Klein scale away from the string scale, from the horizon, right?
Yeah, it's mainly Klein scale away from
Because that's, the whole point about the microstate geometry things is where do you see a difference between a black hole and a bubble geometry? And the answer is exactly at the compactification scale, which could be large.
Yeah.
So if you believe in large compactification scales, like some of the phenomenologists, then the new physics emerges at the Klein scale, which is the same thing here.
Yeah.
So the minute it starts exploring non-trivial geometry, it blows up.
Yeah.
Right.
So here essentially we did the string propagation, where we measure the mode production when the string was feeling extreme tidal force. We measure the effective mass that is produced by this mode production, and we saw that the maximum height here is completely independent on the energy of the string, which is non-trivial. So if you send a nuclear bomb or a tiny pitch, it will bounce at the maximum height, exactly like yours. The only thing is we get exactly like yours. The string needs to be a certain energy, much smaller than the string length, but it needs to be above a certain energy to feel tidal force. Okay, so then just to explore questions.
That's very important for things like Mathieu's talking about, because he has the experience of macroscopic particles versus soft photons. So the whole point is that you better not get very, very soft probes being destroyed, because you should be able to see them. That's how you measure the microstructure.
Okay.
So that's something Samir about. It's very.
If you lower something very, very slowly to just land on the cap. If you just, that's a soft. If you just lower something slowly to just land there and stay there.
One of the things we've been talking about a long time is what's the experience of falling into a microstate geometry or a fuzzball. And if you're a macroscopic person like you or me, you get destroyed into it very quickly. That's the sort of picture he has.
Yeah.
But if you probe it with Hawking scale quanta, things that are very, very, very soft, you can ping off it and you can actually start to measure structure.
Okay.
So you're finding the same thing here, which is really cool.
Okay, yeah. So here, essentially, I reproduce the thing that Nick, Emil, people have been doing. But here, the thing which is slightly nicer is because we are away from supersymmetry, we don't have this atypicality. Everything is confined at the cap. Everything is confined where you expect to have new physics from microstate. Okay, so I would just leave it there and put look here.
I mean, that's sort of so I was thinking about sort of what would happen in non-extreme cases. But I expected the same sort of thing in the sense that because in the supersymmetric case, you've got very, very long ADS logarithmic front.
Yeah,
so all sorts of things can happen there. Whereas if you have an ordinary short star like black hole, the infall times are shorter. It's a rational expression. So the only concern I had, which you've answered nicely, is that maybe it won't experience those forces for long enough to destroy it. Because if it's only happening with an epsilon on the cap, it might have enough time to give an impulse to blow it out. But that's great.
Yeah, for me, also when I was doing that, I expect the same thing. So that's why I wanted to be low. But here there is a huge conspiracy for everything to happen very strongly, very short time, but still like completely stuck.
That's fantastic.
It's
the impulse.
Really the
impulse that matters.
Yeah. Okay, so
it's fantastic.
Okay. More questions from the audience first. I wanted to ask a question about these W transformations and the P transformations and so on. So one of them, I start from an object which is like a D6 brane, has a mass and has a nut charge.
Yeah.
If I have a D6 charge, I can just dualize myself around and I can make from a mass with the D6 to I get a D6, D4, D2, D0.
Yeah.
But I still have a 16 supercharged object. I have a single D brane. It's not a 2-charge solution or a 3-charge solution, just a single D brane.
Yeah.
Is that what the P? So that's the topological star for no. Is that what
you're starting with the supersymmetric?
no, supersymmetric with empty space? Just the one you have, yeah.
So D6, but no
So
external.
it has D6 non-extremal.
Yeah.
And then I just dualize my D6 to death, and I can get a D6, D4, D2, D0.
Yeah.
But with the right ratios, such that if it's extremal, it's supersymmetric, 16 charge. So it's like a single D brane.
Yeah.
Pumping to a black hole. So if I have an empty Schwarzschild black hole in the D brane, but not a D6 alone. If I have a D6 alone and I put it in, I get the solution above. But if I get a D6, D4, D2, D0 and I throw it in, I get the solution. That's the one which is, I guess, the W topological.
This one is really rotation.
The topological star is not like that, though. The topological star.
The P group corresponds to boost anti-dualities, where the W group corresponds to to rotation and dualities.
So the P group, so the topological star is not like that. The topological star have a black hole, and then I put one D4, and then put another D4, and then put another.
You can also start with this solution. You take actually the topological star is n equal to 0, so I don't know. You start with n equal to 0 and you generate from the mass, just from the mass monopole, you generate.
Oh, so this is just the boost rotate. Boost rotate.
Yeah.
So this can give me charges, but no Chern-Simons terms.
Yeah.
Uh-huh. And the other one gives you Chern, but the Chern-Simons and the double topological star, you get Chern-Simons terms. You get
Because you have all magnetic electric parts. Like topological star is only magnetic.
I see. I see.
M5, M5, M5.
And to get the internal product of the charges to be finite, you get a finite Q0, Q6. I mean, you have a finite. I mean, no, if you compute the self-symplectic invariant Q0,
Yeah.
Q6.
For topological star? I think it's,
No, for the double topological star.
I don't know the value now. I guess it's independent of the rotation.
I guess you don't because you have the Rashid. So you cannot get, for example, the Rashid Larson.
You can get the Rachel Larson from these techniques.
You can get the Rashid Larson
Yeah, show and compare the obtain Rachel Larson from.
from the double transformation.
I don't know, not from the W, no.
Oh, okay.
Yeah,
Okay.
but from other like Z or whatever crap.
Okay. Are there any questions online? And people online here?
I guess it can.
Can people online here?
Yeah, yeah.
Okay. Okay, so we'll take a break for 15 minutes and we'll resume at 3:30 with a talk by Alejandro. We'll have the Zoom. We'll have the Zoom.
Okay, well,
The Zoom is there, yeah.
you need to make him.
Actually, if you take your computer,
Yeah.
can you leave your computer and then I can put Alejandro's talk on connected to that. So then we have it on two screens.
Yeah, I agree.
Because on the left one, the Zoom is cutting a bit. So
Yeah.
there's something in the chat. One thing. So if you just keep the Zoom on,
Yeah.
it'll be great. I'll keep the YouTube running so you guys don't do anything. Don't say anything funny.
Wait. What's happening there? Wait. He's doing that for.
No, because you're not featured anymore.
I know because
You're
yeah,
on
you need to
Spotlight.
share. You need to share.
No, you're on Spotlight.
Yeah,
No,
okay. Yeah, I'm coming.
it's all off. All the side, everybody's silent.
students, stuff like that. Like how we-
So Alejandro, can you start sharing the screen? We cannot hear you.
Yeah,
Oh.
so no, I'm muted.
Perfect. Okay, so let me start highlight. Let me start. So go ahead and share your screen, and we'll highlight
This
you
is the-
on the Zoom.
but you cannot.
Oh.
You can do this.
Oh, this is Pierre's solution.
It does. You can do this.
Spotlight for everyone.
Okay, it's not a problem.
Can you see?
Yes, we can see and we can hear.
Should we just wait a minute or two?
Yeah, let's wait a minute until everybody comes back from the coffee, but we are good.
You'll see. Sure. Yeah. This is fine. You should accept. I remember when I was PhD, my first few talks was kind of tough. Like you have a hard time conveying an idea. You have a hard time making things kind of. It's kind of common for you. You don't expect the PhD to be so good to give talks like the first one.
Yes, even if you're a native English speaker.
Yeah. So like doing nice paper, I think, is giving nice notes from the top one.
The other thing is, it's a skill set where you pick out the things that maybe we tell a story, and you pick out the elements and maybe tell the story nicely without getting stylish.
Yeah, but some like here for me, that's why I don't look at the stories boring. Remind me of the totally post-Newtonian expansion and stuff where everything is about text, so it is. If you want to hide, like, I would be happy to just give a solution here to forget about how.
But then you have to give enough trail of breadcrumbs.
Okay, so we'll have the second talk of this afternoon, and we are very happy to have Alejandro Ruiperez from Tor Vergata, who will be telling us about rotating topological stars.
Okay. So first of all, thank you to Joseph and Nick for giving us the opportunity to discuss this work on rotating topological stars with all of you. So as you may know, this is the result of a collaboration between myself and Massimo Bianchi, Giuseppe Di Vitetto, and Francisco Morales. So I wanted to start with what I think is perhaps the main motivation, although not the only one, of the group here in Tor Vergata to study and to look into these kind of solutions. And this is to investigate what would be the potential signatures in gravitational wave signals that this kind of horizonless compact objects could leave. So as you know, nowadays we are testing gravity in the so-called strong field regime, thanks to gravitational wave observation, gravitational wave signals coming from binary black hole mergers and neutron stars, and this has the potential in the future of turning researching in gravity into a data-driven field, which of course would be a very interesting and exciting opportunity. So usually when you compare theoretical predictions against experimental data, we assume first that GR is the theory that rules the gravitational dynamics. So solving the two-body problem is already complicated enough there in GR to go beyond. And second, you assume that the sources that produce these gravitational waves are black holes, this one of them, and that those are well described by the Kerr solution, which is a result of the uniqueness theorem that hold in GR. And this sometimes goes under the name of the Kerr paradigm. So, however, there is a natural question that one can ask in this context, which is if we can use gravitational waves to learn about fundamental aspects of the gravitational interaction. So the first thing that one has to do in order to do so would be to understand what kind of theoretical prediction do you get if you drop one of these two or maybe the two assumptions. So essentially we have two avenues that may or may not intersect each other. So the first would be to modify the dynamics of the gravitational field. For instance, one can think of adding some kind of higher derivative interaction terms to the Einstein-Hilbert term. And the second would be to modify directly the sources. So, for instance, I have in mind replacing black holes by some exotic compact objects or some black hole mimics. So those are, by definition, objects which are very compact, which are regular, and which have no horizon. So the study of such objects has a long history of more than 2 decades, and even more recently, people are making a big effort to understand what would be the potential signatures of these objects in gravitational wave signals, such as echoes in the ring down and tidal deformability and so on. So probably many of you have heard about many bottom-up models, such as boson stars, grav star, wormholes, and many more with even fancier names. So somehow independently, also a large subset of the community working in string theory have worked in the so-called fastball proposal, originally put forward by Matur, and which whose main idea is that at least some of the black hole microstates can be described in supergravity in terms of smooth horizonless solutions. So the nice aspect of this fastball proposal, as compared to other more phenomenologically oriented models, is that the ingredients that you need to construct these smooth horizonless compact objects are already provided naturally in string theory. So they come almost for free. So namely, the ingredients are higher dimensions, because you have to evade no-go theorems in 4D, and also fluxes threading topologically non-trivial cycles. In addition, you have supersymmetry, which has been crucial to systematically construct very large classes of microstate geometries. Here we are interested in non-supersymmetric microstate geometries, or at least non-supersymmetric horizonless compact objects. So dropping supersymmetry is the task become much harder. Indeed, the first attempts to build microstate geometries non-supersymmetry black holes didn't quite work, as Pierre was saying before. So although you can construct the solutions, they cannot have the same charges as the black holes, and in addition, some of them, such as Heidmann, has other problems, such as ergo region instabilities and large instabilities. However, we have heard about recent developments that have allowed to circumvent some of these issues. So I am going to focus on a particular type of a solution, which is these topological stars that we have already heard about, which is a non-supersymmetric horizonless compact object, which has many appealing properties. So in particular, it is compact enough to feature a photosphere. It is simple enough to be amenable for studies of their dynamical properties. There is also a regime of the parameter in which it seems that it is linearly stable, and moreover, it can be easily embedded in string theory and everything. I will comment a bit on these properties later on. So more concretely, the goal of this talk is to discuss a rotating generalization of this solution by Pierre and Ibrahim Abba. Although, just to be clear from the very beginning, I will not claim that this is the microstate of anything, and neither that it is more or less interesting for phenomenological aspects. So this is more or less the plan of the talk. I will start with a brief review of the static case. Will make some remarks. Then I will move to the central part of the talk, which is to discuss the new solution and its properties. And finally, I will conclude with some remarks. So, okay, so I will consider directly n equals to supergravity, minimal supergravity in 5 dimensions, although for the static case, the Chern-Simons is irrelevant. So this is the bosonic Lagrangian. The bosonic field content is at the metric and the vector field, the graviphoton. And there is this very simple solution, magnetically charged solution, which just depends on 2 parameters, Rs and Rb, and these 2 functions, which are given by these expressions. So the magnetic charge is not an independent parameter; is given by the square root of the product of Rs and Rb, and this coordinate is taken to be compact, so it parameterizes a circle with asymptotic radius Ry. So we can distinguish 2 regimes of the solution. So the first is when Rs is bigger or equal than Rb. And here the solution has an event horizon, and it indeed describes a static Planck string, which is known from long ago. It was studied in the early 90s by Horowitz and Strong. So in this case, the U1 generated by parcel Y can be seen very easily, that never degenerates outside the horizon. That's what it is called a Planck string. Then what Pierre and Ba realized is that in this regime, Rb bigger than Rs, the solution describes a smooth horizon-less soliton, which they call topological star. So in this case, what happens is that the U1 generated by parcel Y degenerates at R equals Rb, which is no longer an event horizon, but rather is a cap where the solution smoothly, where the space smoothly ends, if you impose this condition here on that relates the parameters of the solution to the modulus, to the radius of the internal circle. So this is the picture that you have. So you have some R2 smoothly closing at the cap where you have an S2. This is actually very reminiscent of what happens with an Euclidean black hole. Indeed, when you set Rs to 0, you just have Euclidean Schwarzschild times Lorentzian time. So the solution has this topology, Rt times S2 times R2. S2 times R2 is the topology of both Euclidean Kerr and Euclidean Schwarzschild. Okay, so an important issue, relevant especially for phenomenology, is that because of this regularity condition, the solution only exists if this modulus is bigger or equal than certain minimum value, which is around 5 times the Rs, as you can see from this plot, which is just a plot of this function here, as in terms of the quotient Rp divided by Rs. A possible way out to have a smaller radius, internal radius, is to allow for conical singularities in this R2 transfers to the cap. So as I said, one of the nice features of this topological star is that it admits an embedding in string and M theory. So I am going to consider just the embedding in 11-dimensional supergravity, where it turns out that it appears as a limit of equal charges of a non-BPS intersection of mutually orthogonal M5 rings. So this is the solution I am referring to, the 11-dimensional solution. So when these functions W1 and 2 are set to 1, we just have a BPS solution describing 3 stacks of mutually orthogonal M5 rings. Then you can turn on this blackening factor, often called, and also this one here. And when you set, also this is a solution provided that these parameters here are determined in terms of the parameters of the harmonic function in this way. And what the nice thing is that when you set the three charges equal, this thing here, the internal part factorizes, and you just have some 5-dimensional geometry times T6, and it turns out that the 5-dimensional geometry that you get is precisely the topological star or the Horowitz-Strominger black string solution. Although it seems that there is one more parameter, it can be eliminated with a shift of the radial coordinate. Okay, so in the last years, there have been a lot of effort from many groups in trying to explore dynamical aspects of these solutions. So, in particular, people have looked at the shadows, at the tidal deformability, scalar gravitation, and electromagnetic perturbation. And more recently, Massimo, together with Donato Vini and Giorgio Di Russo, have looked at the emission of scalar waves and some self-force stats. So interestingly, the outcome of these quasi-normal mode studies is that the solution is fully stable, at least at the linear level in this regime. While for RB bigger than 2 times RS, we show, and also this paper discusses this, that the solution has Gregory-Laflamme instability. Okay, so now I move to the core of the presentation. So the starting point is a solution of, again, minimal n equals 2 supergravity in 5 dimensions, which was found years ago by Compere and collaborators. Actually, this is a rewriting of their solution that allows you to write it in just one slide. So it has 3 independent parameters. So 2 already appear in the static case, which are RS and RB, and then there is one more rotational parameter, which can be taken either AS, AB, or this A square. So they satisfy these 2 constraints here, so there is just one independent. Also notice that only A square appears in the metric, so I am saying this because then we will consider a regime in which this is negative, but there is nothing becoming imaginary in the solution. And here we are using chi is cosine theta, so using this parameterization. So the way in which Compere and collaborators found the solution is similar to what Pierre explained. They started with, so they use a solution generating technique, starting with a Kerr black string solution, depending on 2 parameters, reducing it to 3 dimensions, exploiting the isometries of the solution, and then acting with some G2 transformation that depends on the 3rd parameter. So in the original form of the solution that they wrote in the paper, the solution only covers the regime RS bigger or equal than RB, in which they showed that it describes a magnetically charged Kerr black string, which a rotating generalization of the one by Horowitz and Strominger. So the main advantage of the parametrization we are using is that we can analytically continue the solution into this regime, RB bigger than RS, and also for free it comes that it is invariant under this sort of double big rotation, just as in the static case. So no limits of the solution are Kerr times a circle, which is what you get when you set RB and AB to 0. Euclidean Kerr times RT, where T is the Lorentzian time, which is what you get when you set RS and AS to 0. And then when you set the rotation to 0, you switch off the rotation, you get the 2 solutions I already discussed. So the static black string and the topological star. So now the question is whether this solution by Compare et al. What does it describe in this regime, RB bigger than RS? So what we are going to show is that, as in the static case, it describes a horizonless topological solid. So in order to do so, consider this Killing vector, which is just a combination of the three isometries available in the solution, and these are just constant coefficients depending on the parameters of the solution. So actually, this is proportional to the generator of the horizon, which appears in the black string regime, of course. And I am saying this because it may help you to see that that the norm of this Killing vector vanishes at r equals r plus, where r plus is this quantity over here. So in this regime, RB bigger than RS, using these two relations, one can show that first A squared is negative, as I was saying before, which implies that the argument of inside the square root never becomes 0. So there is no analogous to the extremal limit in curves in the curve solution. And also it implies that there is this hierarchy between the between the three radii. So R plus is bigger than RB and bigger than RS. Okay, so now what we want to show is that this hypersurface R equals to R plus. In this case, it no longer represents an event horizon, but rather a cap where space ends. So to see this, what you have to do is one way of seeing this is working in coordinates adapted to the isometry. So this is more or less a standard. The key thing is that now the Killing vector can be just written as partial of some coordinate y prime, and then we expand the geometry near r equals to r plus, and keeping the relevant terms, the relevant and the leading terms in rho, where rho is this combination of r minus r plus, you get this geometry here, where gamma is this expression here. So you may recognize this first factor because this appears already in the static case, and this is the correction due to rotation. So when rotation is absent, R plus is just RB, and then this is 1. So now we demand regularity of this near cap geometry. So this is equivalent to saying that this is a smooth R2 factor, which implies that the coordinate y prime is periodic with period 2 pi gamma. So up to this point, this is pretty much the same to what happens in the static case. So let us now discuss what are the main difference. Yes.
Yeah. Okay. Y prime depends on t here.
Y prime is actually equal to y. So there is some t prime, which is t minus some constant times.
Yeah, some static time. Does it depend on the initial t?
Y prime, no. T prime depends on y. There is some t prime, so the metric induced at the cap can be written in terms of some t prime and some phi prime that are just t and phi minus some constant times y.
Okay. So t prime is periodic.
T prime, no, T prime is not periodic.
So t is periodic then.
Sorry?
So t is periodic. If t prime is not periodic.
At this point, only y prime is periodic. Well, of course, phi prime. Fine.
Sorry?
At this point, only I haven't assumed anything about the periodicity of the other coordinates. So only y prime is periodic.
Yeah, but if you're saying that t prime depends on y prime, it means
no. Okay, the coordinate the prime coordinates are just t prime, y prime, and phi prime. And t prime is not periodic, and you have that phi prime and y prime are periodic. So of course, phi prime is 2 pi periodic. Otherwise, you get conical singularities in this metric. I don't know if you can see the.
Like if t prime is not periodic, but t prime is like t plus some y prime, it means that t is periodic then.
No, it's not periodic t. But anyway, what you're meaning is that this identification here, when you write it in terms of the original coordinates, involves a shift in t.
Okay.
Yeah, that's correct, but this doesn't mean that t is periodic. Anyway, I am about to say how you remove this. Okay. So what you have to do. So well, in order to see the main difference with respect to the static case is to go and study the asymptotic geometry, and precisely because of what Pierre is now pointing out, it is convenient to work with these hatted coordinates, which are just obtained by boosting the solution along y. And the reason why we are doing this was the circle defined by this identification here, when you express it in terms of t and y, involves a shift in t, phi, and y. So in other words, the problem is that the original Killing vector has a leg along t. But when you do this transformation, now you can write the Killing vectors as the Killing vector t as a linear combination of partial y hat and partial phi. Okay. Anyway, in terms of these hatted coordinates, the asymptotic geometry is this one leading order in R. So it is asymptotically flat. But the issue is that now, when you write this identification in terms of these coordinates here, you get these twisted periodic identifications for phi and the new y coordinate. So this is the usual identification for phi, and then this second one comes from this regularity condition here. Okay. So at this point, the orbits generated by partial y hat are not closed. Don't close, because this is a combination of chi and phi, which have both closed orbits. But if you don't impose any condition, the orbits of partial y will be dense in the torus generated by chi and partial phi. So the general condition that ensures that the orbit of this Killing vector close is that this quantity here is a fractional number. So h and q are integers. Indeed, if you plug this in this identification, you see that these two imply this third one. So now, once you impose this condition, this quantization condition, the orbits of partial y close. In the general case in which h and q are coprime integers, then you have that the boundary is RT times S2 times S1 mod CQ, as already Pierre said. Okay. So from now on, I will just set the H21 because it's not important at all. So now so clearly this is not, we would like to avoid this twist in the boundary. So we can ask ourselves if this is possible. So the answer is no. If you impose that you have a completely smooth geometry. But if you relax this, introducing a conical singularity in the R2, then it is possible to avoid the twist if you. So the reason is that if you demand a completely smooth solution, then as I discussed before, you have this condition, Ry equals to gamma. This was this function of the parameters, and then plugging this into this relation here with h and q equals to 1, gives you this condition, but this unfortunately doesn't admit real solutions. However, we can allow for conical singularities. So now Ry is gamma times 1 plus delta, where delta is the conical deficit or a sex angle. And then the quantization condition, this quantization condition becomes this, and this can be admit solutions for delta bigger than 0, which would represent a conical stress. I am just mentioning this because I don't know if it might be interesting to further look at this, but in any case, in the remaining of the talk, I will just concentrate on the regular case. So, okay, so let me summarize. So the solution that we have found, once you fix, let's say, the boundary data, so the modulus Ry and the integer q, we are left just with one independent continuous parameter that you can think of it as being Rs, or you want the mass of the solution. Then the remaining two, the magnetic charge and the angular momentum, are solved by solving these two conditions. So remember, this was coming from the regularity condition, and this comes from the fact that the orbits of parser y close. And well, just to compare with the static case, I plotted here the internal radius as a function of RB, of the quotient between RB and RS, and essentially you see kind of the same features with a slight improvement in this rotating case. Okay, so this is the phase diagram that you have. So here in the x-axis, we have this quotient between RB and RS. And here, this dimensionless rotational parameters, so AS divided by RS. So between 0 and 1, here in this orange region, you have the non-extremal magnetically charged black string studied by Compare and collaborators. Then this green line represents the extremal limit of the solution, and beyond this, you have a naked singularity. So this is the point where the argument of the square root in the expression for R plus vanishes. Then for RB bigger than RS, as we just saw, you have this rotating topological soliton. So this line would be the solution by Pierre and Ibrahim Abba. And finally, this vertical line is quite a curious solution, which I was not aware of. So it's also an extremal solution, but it's different from this one here. And well, I forgot to mention that this extremal solution connects the extremal Kerr solution and also the extremal Horowitz Strominger black string. Okay, so now let me move on and discuss a bit some properties of the solution. So the first thing we looked at was the region, because of there is this famous result by Friedman saying that in GRs, solutions featuring an ergo region but with no event horizon are linearly unstable. Indeed, this is it is known that non-supersymmetric some non-supersymmetric horizonless solutions such as JMR suffer from this type of instabilities. And even Eperon, Real, and Santos argued that they may appear even for the supersymmetric ones. So in this case, you don't have an ergo region, but you have the notion of what is called an evanescent ergo surface, and this has been argued to lead to nonlinear stability. Nicely, the solution that we have just discussed would avoid this potential ergo region instabilities, because actually there is no ergo region. So you can show that this killing vector, partial T, is everywhere time-length. So another potential worry when you construct a rotating solution would be the appearance of cross-Stanley curves, but we also checked in the paper that they are also absent in this solution. Okay, so now I am going to discuss the dimensional reduction to 4 dimensions, which is kind of the controversial part of the work. So, well, there are two, in principle, there are two natural U1 isometries along which you can reduce. So the first is to reduce along this killing vector, G, the one that degenerates at the cap. But this has the problem that it leads to a solution which is not a 4-dimensional solution, which is not asymptotically flat. This is actually equivalent to saying that the Kaluza line scalar diverges at large R. As Pierre pointed to us, this is this kind of solution was known. It is called a magnetic flux tube and was studied by Doker, Gauntlet, Gibbons, and Horowitz. However, as they discuss in the paper, one could also consider reducing along a linear combination of this vector T and partial phi, as long as this linear combination has closed orbits. One such example would be just partial y hat, as we saw. And when you perform such a dimensional reduction, you end up in a 4-dimensional solution, which is asymptotically flat, and which furthermore has the same asymptotics as Kerr up to order 1/r squared corrections. You can use this to read the U1, the 4-dimensional mass and angular momentum. So there is so the origin of the controversy is, I would say, this a subtlety that arises when you reduce along this direction. So in order to explain this, consider this mode expansion for a scalar field. So now, well, these are I define this RS to be the radius of the circle parameterized by the coordinate y hat, and then using the identifications of the coordinates, you get that both m and n must be integers. But on top of this, you have this relation here, which tells you that n is equals to m plus q times some other integer, which I am calling m prime, which means that you are restricted to n equals to the lowest kk mode, n equals 0. Only modes with not all modes with m, not all m modes are allowed. Only those with the right, let's say q parity. So for instance, for q equals 2, only the even ones would be allowed. However, I am not convinced that this is signaling any inconsistency in the dimensional reduction, but rather is pointing us that you have some that you are reducing along. So you are reducing a solution which has these properties of the twisted bundle, and this is how the 4D solution would know about this.
Sorry, stupid question. You don't have periodic time when you do the second reduction?
No. No, the coordinate y hat doesn't. Sorry, t hat doesn't enter in the periodic identifications anymore. I've done it on purpose.
But t hat is defined. Sorry, can I go back to the t hat? I'm a bit confused.
T hat is precisely defined. This is the definition of t hat. Is precisely defined such that the periodic identification do not involve t hat anymore.
Yes, but then because Y is periodic, T hat is going to become periodic. Y has its own periodicity, right? Or
No,
not?
No, Y no. Y is not periodic.
Oh, why is it? Okay.
There is a combination. There is a combination. So the identification are these ones. You can rephrase it in many ways. But by the way, I noticed that this kind of boost were also done in the past to construct some horizonless microstate geometries by Justo, Matura. So it's the same trick. They did it in a different way. So they first boost the solution and they fix the boost parameter in a way such that you don't have cross-like curves. I am directly fixing the boost parameter here. But this, I think, both approaches are actually the same.
Okay, thanks.
Okay. Okay, so anyway, this kind of discussion, I think, are a bit artificial because actually all the dimensional reduction that you can do are pathological because you are reducing always along isometries that have a non-trivial fixed locus. So at the end, you end up with a four-dimensional solution which has some naked singularities on that breaks down at some point. And this is the case both here and of course in the static case, which just say that the solution are 5-dimensional, insisting in viewing them as a 4-dimensional solution has problems. Okay. So then we started exploring a bit some dynamical properties, although we did some preliminary studies. So the first thing we looked was the geodesic motion around these rotating topological star solutions. So what we saw is that as in Kerr, the geodesic motion can be expressed in a decoupled first order form, where here PR and PK are the radial and angular momenta, and EP and J are constants of the motion. Mu is the mass of the particle, the test particle, and K is the analogous of the Carter separation constant. Then we studied the light rings with P equal to 0. So in general, they are non-planar, except you restrict to the equatorial ones. Which are planar. You set the Carter separation constant to plus or minus J. So the plus correspond to co-rotating orbits and the minus to counter-rotating. So then what we saw, at least in this very preliminary study, is that it has very similar features to the static case. So you get some correction to the critical radius, which depends, of course, on whether you are co-rotating or counter-rotating. And well, here the dots are just because this is valid at next to leading order in the rotation parameter. We also look at scalar perturbations at equation, at least. So we consider a massless scalar perturbation in the background of a rotating topological star. So this is the equation of motion for the scalar. Given the isometries, it's natural to write down this kind of answer, where S and R are functions of the angular arm of theta and the radial coordinate. And essentially, this is the same as as what I said before. Because of the identifications of the coordinates, you have this non-standard quantization condition that tells you that for p hat equal to 0, only certain M modes are allowed. Then you plug this ansatz into the Klein-Gordon equation. You find that it leads to two second order ordinary differential equations for the functions R and S, which where here A is also a Carter-like separation constant, which is different from K, and this is just some functions of the radial coordinate. Interestingly, both are instances of both differential equations are instances of confluent Heidmann equation, which people at Tor Vergata like very much because they can be studied using these gauge theory techniques, and this would allow them to would allow us to apply the same techniques as in the static case to address the calculation of the quasi-normal modes and other dynamical properties. Okay, so I am almost done. So let me conclude. So we have found a rotating topological soliton that generalize in a certain sense the static solution found by Pierre and above. Unless one introduces conical singularities, the solution only exists if you have this twist at the boundary. So we have shown it has no ergo region, therefore no ergo region instabilities, and also no closed-like curves. And we have studied geodesic motion, showing that it is separable as in Kerr, and also that the scalar wave equation is separable into radial and angular parts, which are both of confluent Heidmann type. As I already said, an obvious future direction would be to study scalar perturbation, discuss stability, and so on. But also, I think it is worth. So I think these solutions are interesting per se as gravitational solitons, and indeed, I think it would be worth to study it from the point of view of the Euclidean path integrals. So I think it is a certain point of the Euclidean path gravitational path integral, and actually this interplay has been shown recently to happen also even for the supersymmetric 5D microstate geometry. So they are closely related to the others that account for the entropy of supersymmetric black holes. So I think this is would be an interesting thing to look at in the future. And that's all. Thank you.
Thanks. Okay, so can we get back questions? I guess, I don't know, Pierre.
We already discussed that.
No, but we want to understand also what the discussion is.
I wanted to actually ask, just to maybe start that off by just simply saying, some of these solutions are sick and some of them aren't. Which ones are the good ones and which ones aren't?
The static ones are.
Okay, no, I understand the static ones. Are any of the rotating ones good, or are they all got some strange?
There's a twisted periodicity which screw the boundary.
Sorry, Alejandro, can you hear us or?
No, not very well.
Okay,
Where's the microphone?
There's no microphone, just.
We just need to speak.
Maybe, Joseph, if you repeat the question, maybe I can get it because I can hear you a bit better.
So I have a question really about the work that you and Pierre were doing, which is some of these things have strange boundary conditions. Are there any rotating ones that don't have strange boundary conditions? Because in your talk you said these are sick and those are sick, but I want to know whether anything survives apart from the static ones.
JMAR doesn't have this because essentially in JMAR, what happens is that this condition here can be solved for. I mean, the problem here is that you don't get a real solution, but in JMAR you have an analogous condition. Actually, I think you have two, and you can solve them, and then you don't have this problem with the twist. So the idea in JMAR is essentially the same. Is you make some U1 string, and in general, when you have rotating, it's the same as what happened with Euclidean rotating black holes. The boundary is twisted,
The boundaries.
So in Kerr, you do in Kerr the Euclidean time and phi satisfy twisted periodic identifications. So this is the origin of this problem. But in the case of Heidmann, you can impose a quantization condition, which essentially, if I translate it to Euclidean Kerr, would be that beta times omega is some integer, and then you untwist the identification. Here we try to do this, imposing this condition, but unfortunately, it's not. That doesn't work. So it's a matter of the case of luck. I don't know.
The conical axis is in the middle at the Euclidean horizon.
The conical SX is in the tip of the R2 here. So it's transverse to the.
I see.
I was wondering also, did you derive the mass using comma formula and stuff like that? Did you get a phase space with mass, charge, and stuff?
Yes, we derive it using 5-dimensional comma formulae. I haven't shown to you the expressions, but we have in the paper.
Does it match your weird 4D reduction?
Sorry?
Does it match your weird 4D reduction?
No, of course not. But not even the static case.
What?
No, yeah, because the Kaluza-Klein scalar contributes to the mass. If you compute it in 4D and in 5D, you don't get the same.
And just in terms of phase space.
In 4D, you get RS plus 2 RB or the other way around. I don't remember. No? If you do it in 5D, you just get RS. And the RB comes from the warping, from the Kaluza-Klein factor.
I didn't do the computation yet. I don't know.
So that, yeah.
So if you do the second compactification, can you go back to the second version? So again, one of them gives you Melvin. If you compactify again up on the so one of them. Okay, so I'm here. I'm in 5 dimensions. So the first one gives you Melvin if you reduce along dy plus some d phi because it's a magnetic flux tube, and then the second one, but the solution we are reducing, is it okay in 5D or is it has a conical axis? I just want to know what's the.
Now here the solution in 5D. I am only considering the regular one. So no, it's
regular solution in 5D and you reduce it along dy tilde.
Yes.
What's the problem? I just want to know.
I mean, in KK theory, you need to reduce something.
The issue of Pierre is this.
No, this is not the only issue. I'm sure there is more. Here is one I pointed out. But,
can you come in front? Sorry, Pierre. I want to understand the discussion. So.
I mean, like you compactify along an orbit which is not independent. In a sense, moving along y bar makes you move along phi. So you cannot reduce along that.
Pierre, you agree? I mean, because
I don't want to come back to this discussion, so maybe.
But we want to understand the discussion, so let's have the discussion.
I mean, it's well explained in Docker countlet Gibbons already. Like you need, if you have something with twisted periodicity, you need to compactify along this zeta function. If you like KK
killing spinner, you must compactify on a killing spinner.
Yeah, but not only it is also like a dy bar is also kind of a killing spinner.
You can write on your screen. Your
it's
shared. So
yeah, I mean
you can write on your screen.
I mean the thing which is like the KK theory is like you have a higher dimensional theory. You do something to get duality with a lower dimensional theory. Doing it correctly is reduction on zeta. I don't know how it's called, zeta, whatever it's called. If you do it along dy bar, I mean, you can do it whatever, you can apply the rule, but the lower dimensional theory is not dual in any sense to your higher dimensional frame. So this solution, if you like, in what I pointed out in the next slide, like what Alejandro was saying in the next slide, is just saying that if you do stuff with this 4D guy, it's not dual in any sense with the 5D guys. In a sense, if you do the scalar wave perturbation on your 4D reduction, you will never find that M is quantized in QZ.
I mean, this is something that you must impose.
Yeah, but this is something you derive in your 5D frame. But if you like normally Kaluza-Klein theory is telling like whatever perturbation, massless perturbation in 4D or 5D should be dual. It should give the same answer. But here in 5D you obtain that M is QZ. If I take your 4D metric and I study box phi, I will never obtain that M is QZ. M can be anything. So just saying that it's not dual. You can do it, but it's just not. It's not something where if you study perturbation in your 4D guy, it's not in any way related to the perturbation in 5D. Just because you have to apply the real KK reduction. But again, I mean, this is something we discussed.
But why can't I just stay in 4D and I impose a set of rules? I have a solution which is a.
What do you mean? I mean,
What's wrong with the 4D physics? So you're saying that now?
you know, there is nothing wrong if you compactify along the right direction.
Sure, but then I'll get Melvin. In their case, I get Melvin. So I mean,
then if you compactify along anything else, there is no duality. So it's just okay. I have a space-time, but if I study perturbation in this 4D guy, it's never related to my perturbation in 5D.
I mean, it is if you restrict to the modes which have the right Q parity.
Yeah, but here is a point I pointed out because it was an easy one, but there might be more subtleties, like other stuff.
Okay, if there are other subtleties, then I just don't see them. I must say I was very much confused by this for a long time. But actually, it's true that if you restrict to these modes, the perturbation that you get both in 5D and 4D is just the same. And,
okay.
And it's true, and it's also true that these are just different slices of the same. These are just different slices of the same 5D geometry.
Yeah, I need to think, but I mean, already this one is pretty pathological.
What's wrong with QZ? So Q is a number, right?
M is a spherical harmonic. So usually, like in our world, we can.
YLMs.
Yeah, YLM. But here, if you have a topological star in Andromeda, you cannot do M equal to 2 here.
You're far away. You cannot do M equal to 2.
Yeah, even at infinity.
You can do it here.
No.
M equals to 2 around here.
No,
you cannot do it there.
I mean, it's just like
there's no. I mean, you need to define the file
Yeah.
Andromeda. You need the file along Andromeda. Sure, if you have a screwed up file along Andromeda, there it's a bad file. But here I'm far away. I mean, I can do it. I mean, I need the mode to see this.
Yeah,
I need the mode which is phi equals to 2.
Yeah, but I cannot produce a mode which is M equal to 2 leg. This is
in the sky.
Anywhere you should not produce something which has leg along 2, 3, 4, 5. You need only that.
Oh, because you're saying that the space-time only accepts modes which are.
Yeah, it's kind of a weird thing. But I don't know. I have no idea.
I agree that it is a weird, kind of weird thing. Maybe it's not attractive or appealing for Fino purposes. But I am not. I don't think it is inconsistent. I mean, so clearly the 5D physics is clear. I think we'll all agree on this.
Yeah, definitely.
And also, I don't understand. You agree with what Docker, Gauntlet, and Gibbons and Horowitz say in the paper, because they clearly say that you can reduce along any linear combination of these.
Integer, so it will not solve your problem.
Sorry? So the problem, yeah,
it's an integer shift, so it will not solve your problem of 1 over q.
What do you mean integer?
You can shift dy by n d phi.
Oh, sure, yeah.
It will not solve the fact that is dy is shifted by 1 over q.
I know that it's not exactly the same.
Yeah, I agree. I was just wondering if you can derive some phase space, mass, spin, and blah blah blah. Does it live with the same mass and spin as a black hole with the same boundary, even if it's a weird boundary?
Yeah, but the problem is that they don't even match in the case that you have the same.
I mean, you can put the black hole with this weird boundary. You have nothing forbids you to do that.
Yeah, sure. You can do it.
So I was wondering if mass and spin can match the black hole mass and spin, and charge also.
No, sorry. The mass.
Like, let's say you take one example of your topological star here with RS equal to whatever, RB equal to, I mean, everything is regular, blah, blah, blah. And you get M equal to 35, J equal to 2, I don't know. Can you have a black hole with the same mass, spin, and charge?
You are referring to these expressions in 4D or the ones in 5D?
Yeah, assuming your thing, yeah, here.
So in 4D no, but is what I was saying before. They don't even match in the static case.
I mean,
If you compute them in 5D and you put also this weird boundary for the black hole, you will get the same, of course.
No. My question is more like if the topological star can exist in the same regime of mass and charge as the black hole. For topological star, it works, static ones. There is a regime where mass and charge, where both exist.
I don't know. Yeah.
Okay.
We don't even we haven't even considered the black string with this weird boundary condition.
Okay.
So yeah, it would be.
Sorry, if I may just add a small comment. I would suppose that by continuity, because in the phase diagram, this rotating topological stars are connected to the static case, at least for small rotation parameters, it should work.
Well, what do you mean connected? Like, yeah, you can take.
Because you can take alpha to be very small, arbitrarily small. So you can take alpha to epsilon, and then then the topological star and the black hole coexist. And then if you just take up alpha to be epsilon, they should still coexist. There's no reason why they should get out of the black hole range immediately for alpha non-zero. A black hole you can turn on a tiny bit of rotation. It's a non-extremal black hole, so you can start giving it a tiny rotation, and you can give the topological star a tiny rotation. So because they don't have their alpha can be as small as it wants.
I don't know if you can be as small.
Yours can jump instead. So the main problem.
Yeah, exactly. Just by continuity, if it works for A equals 0, it should work.
I mean,
At least for small A.
A is not continuous. It's like if you impose regularity, you have this Q and H, I think is how Alejandro call them. So A is actually quantized, but I don't know how much
but that's a regularity. That's indeed, you need to impose regularity for that.
No, exactly. But I mean, the mass and the charge are connected with continuity with to the A equals 0 case.
Yeah, but A can be big. Like the first A with H equal to whatever and Q to be whatever, it can be pretty big.
For your conditions, but not for theirs.
Not for them also. A is quantized.
No, exactly.
It's quantized. The A's you guys have is quantized. I thought your A can be arbitrary.
What Pierre is saying that it's that these two relations, what I show here, these two relations can be thought of as determining the magnetic charge and the angular momentum in terms of the mass and the boundary data.
Yeah.
But I guess.
But in that phase diagram that you have in the other picture, A can be arbitrarily small.
Yeah, but here it's not. It's like the boundary are different. And it's not a mass spin diagram, and it's not regular. I mean, there is no regularity condition imposed here. I guess.
Well, it's not completely clear.
I mean, the previous condition quantize some stuff. Like there is 1 over Q equal to something.
Yeah. But what is quantized, if you wish, is the A squared and not AS.
What?
A squared is AS squared minus AB squared. AS and AB, I don't think they have to be quantized.
It's not that they are quantized. It's just that they are not independent from the mass. It's like in the topological the static case. If you fix the modulus, the magnetic charge is not independent from the mass.
Sure. But in that phase diagram, we took AS and RB as independent parameters, and the rest fixed in terms of them.
Okay.
So you can have a small, you can start doing it. Okay. Interesting. Okay, let me highlight. Sorry, I'm highlighting. I did for the Zoom.
Yeah. So sorry, everyone. I have to leave. Unfortunately, I will not be here for the discussions.
Yeah. No, I don't think I mean, I don't know if there's too much discussion. So
Yeah.
no, I think that's that was quite clear. And again, thanks to both of you. And I'll see you guys tomorrow then on Zoom for
Yeah, I'll see you tomorrow.
BPS Chaos. Okay.
Bye bye.
Thanks. Thank you so much.
Thank you.
Bye.
Thank you.
Bye.
Bye.
Bye.